This is the demonstration problem for Newton's second law with off-axis forces. The problem is Bubba's pushing on a 10 kilogram block. He's pushing downwards with a force of 60 newtons at an angle of 30 degrees below the horizontal. If the friction between the block and the skating rink is negligible, A, what's the acceleration of the block if Bubba's push has a magnitude of 60 newtons? B, what is the normal force on the block? So the free body diagram looks like this. We're given the space diagram, and so we know the weight of the block, and so we isolate the block. And so when we do that, we look at the forces that are on the block. Two kinds of forces. One is the field force, the only field force or action at a distance, no contact force, is the gravitational force or the weight, which is mass times the acceleration of gravity. And so the mass of this block is 10 kilograms times 9.80 meters per second. And so the weight or gravitational force by the Earth, exerted from the center of the Earth, on the block is 98 newtons, and that is down. Then we consider contact forces. Of course, there is Bubba's push of 60 newtons. It's an off-axis force, and so we must resolve that into x and y components. The x component is hypotenuse times the cosine of the angle, or 60 newtons cosine of 30 degrees. That is a positive x-axis force. The y component is hypotenuse times the sine of the 30-degree angle, and that's a negative force, and so 60 newtons sine of 30 degrees. Then we look for other contact forces. So we've isolated the block, and so we look at anything inside this circle that touches the block, that's contact force. The ice rink touches the bottom of the block, and so we must consider both x and y forces. There is a frictional force as the block slides along the rink. It's parallel to the two surfaces in contact, opposing the motion of one over the other, and that would be a sliding friction force or kinetic friction force. But we have decided to consider that to be negligible, so that does not play. But there's also a vertical or y-axis contact force by the rink on the block, and so that is the normal force. These forces are not concurrent, as their lines of action would intersect at other than a common point. However, we're not considering any possibility of rotation or for the block tipping, and so we must put all the tails at the origin of our coordinate system, and this means only translation is possible, not rotation. And so that will be the center of gravity of the isolated block. That is the origin of the x and y-axis coordinate system. So now we go to the next step of our free body diagram and the final step. Two things are important in the free body diagram. Number one, as we've talked about, is all the tails are at the origin, making the forces concurrent at the origin. And the other is that we have resolved all off-axis forces, in this case only the 60 Newton push, into x and y components. And so the final free body diagram should only show x-axis force components and y-axis force components. And so what we have is the 60 Newton cosine of 30 degrees x-axis component of the push is along the positive x-axis. Along the negative x-axis we have the weight, or 98 newtons, but we also have the negative y-axis component of that push, the 60 newtons sine of 30 degrees force that's down. We have that, and then along the y-axis we also have the normal force. The x component of the push is 60 newtons times the cosine of 30 degrees, and that's 52 newtons, and so we annotate that. The y component, which is negative, is 60 newtons times the sine of 30 degrees, and that's 30 newtons, and so we annotate that. And so now it is time to analyze the free body diagram and then to ask the critical questions along each axis to determine how to apply Newton's second law. And so on the x-axis, the question is velocity along the x-axis is constant if and only if the net force along the x-axis is 0. So remember that the answer to both questions are either both are yes or both are no. So if we ask about the x velocity being constant, it's not obvious. It's not given. We know more about the forces, and so we go to this side of the if and only if. And so we say, are the forces along the x-axis balanced, or do they sum to 0, or do the pluses cancel the minuses? We go to our free body diagram, and we see that since there's no friction, or friction is negligible, the only x-axis force component is the x component of the 60 Newton push, which is 52 newtons, and there's absolutely nothing to balance it. Therefore, we conclude that the net force along the x-axis cannot possibly be 0, and so this implies that the velocity along the x-axis is not constant. And so if the velocity is not constant, then the change in velocity is not 0, and so the acceleration along the x-axis is not 0, and it must be in the direction of the net force along the x-axis, the 52 newtons. Now we go and ask the same questions independently of the y-axis. And so we say the velocity in the y direction is constant if and only if the net force along the y-axis is 0. In this case, since it's a level skating rink, it is the case that the y position along the y-axis is everywhere 0 as it accelerates to the right. And so since it is at rest effectively along the y-axis, then we conclude that the velocity along the y-axis is constant, and in fact it is 0. This means that the net force along the y-axis must be 0, or all the y-axis forces are balanced. This says that the normal force, which is positive, must be balanced by the y component of the push, the 30 newtons is down, as well as the 98 Newton weight force. We have established that the net force along the x-axis on the block is not 0, and therefore the forces are not balanced, and so the velocity is not constant, and so there must be an acceleration along the x-axis. And so our chore is to find that acceleration. It is the sum of the forces, and that comes right off of the free body diagram. The sum of the forces along the x-axis, there's only one of them, that's the x component of the push, the 52 newtons. The second thing it is equal to is mass times the acceleration along the x-axis. That's 10 kilograms times the acceleration, a sub x. And so we solve for the acceleration, and we get a sub x is 5.2 meters per second per second. We also established that the net force along the y-axis is 0. That is because the block is at rest, or at y is equal to 0, along the y-axis as it accelerates along the level ice rink. So the net force in the y direction is two things. It is the sum of the forces along the y-axis, which comes directly from the free body diagram, and it's also equal to 0 since the acceleration along the y-axis is 0 since it is at rest along the y-axis, or the velocity along the y-axis is a constant 0. So the normal force is the unknown, and it's balanced by the weight force, which is 98 newtons, and the y component of the push, which is 30 newtons. That's equal to 0. So we solve for the normal force, which is 128 newtons, which we note is not the weight, as that's only 98 newtons. The end.